Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I'm making my lesson 4 in probability and SMP preparation. And today's lesson I'll be talking about expectation and some distribution properties. So I'll be consider two cases, the expected value for discrete random variable and expected value for continuous random variable. Moment generating function, we'll be talking about mode and skewness and also inequalities. So first of all, expected value of a discrete random variable. The terminology expectation or expected value is basically just indicate the mean of a random variable. So for expected values, let x be a discrete random variable, and so the mean of this random variable is the summation of x times p of x. That means we take x time with its probability, and the expected value of a function of x is summation of h of x times p of x. So here we replace x by h of x. That means the argument here is h of x. So for the first one, the argument is x. The second one, the argument is h of x. So if we have another function, g of x, then e of g of x is just summation of g of x times p of x. And variance and standard deviation. So the variance of random variable x is var of x. This is the notation. Sometimes we use sigma square of x. So it's a notation. So variance of x is ex squared minus ax whole square, and this is summation of x minus x bar whole square times p of x. So the variance is basically to measure the dispersion. So the mean tell you measure the central tendency, but for the variance is measure the dispersion tendency. So here is basically mean that how the data, how the distribution spread away the mean. And the standard deviation is basically just the square root of the variance. So sigma of x is square root of var of x, and that is square root of summation x minus x bar times with p of x. Now expected value of continuous random variable. Let x be a continuous random variable, and the mean, then the mean of a random variable x is just the integral from the infinity to infinity of x times f of x dx. So here, remember for discrete random variable we are using summation, but for continuous we use integral. And expected value of h of x is integral from the infinity to infinity of h of x f of x dx. So it's look like discrete case, but the only thing different is we are using integral instead of summation. Variance and standard deviation, everything will be the same, just using we're going to use integral. So variance of x is ex squared minus ax whole square, and this is equal to integral from the infinity to infinity x minus x bar whole square f of x dx. And the standard deviation is the square root of variance. So that was about expected value of random variables. Now we are going to consider a new concept, moment generating function. So for moments of a random variable, if n is an integer greater or equal to 1, then the nth moment of x is ex to the n. That means expected value of x to the n. And the n central moment of x about the mean mu is expected value of x minus mu to the n. It is worthwhile noting the general form of the integral that appears in this example. If k is non-negative and that is an integer, and a is positive, then by repeated application of integration by parts, we have one properties. That is the integral from 0 to infinity of t to the k e to the negative at dt is equal to k factorial over a to the k plus 1. So here this property you need to memorize in case there's some problem that requires some calculus integration skills, but like sometimes you can like fasten your solving by using these properties. This one can be proved by taking integration part by parts. So we integrate by parts and we can have this property. This is calculus 2 and 3, right? Next, moment generating function of random variable x. The moment generating function of x, MGF, is denoted by mx of t, or mxt, mt, mt, and it is defined to be mx of t is expected value of e to the tx. So in the moment of random variables, we use e of x to the n, but for moment generating function, we have e to the tx here. It's basically the expected value of a function of x, and this is the exponential function of x. So if x is a discrete random variable, then marginal function mx of t is expected value of e to the tx. So the summation of e to the tx px. And if x is a continuous random variable, then marginal function mx of t is expected value of e to the tx. So that's the infinity to infinity of e to the tx f of x dx. And here we have some properties. First, mx of 0 is we basically to substitute t by 0. So we have e to the 0 times x f of x dx. So this is summation. This is integral from the infinity to infinity of f of x dx, and this is 1. So marginal function of a random variable x at the point 0 is always 1. The first derivative of the marginal function, the first derivative of the generating the moment generating function is m prime of x, m prime x of 0, and this is expected value of x. So the first derivative of the moment generating function is the mean. The second derivative of the moment generation function at the point 0 is e of x squared, and we have the n derivative of the moment generating function is expected value of x to the n. So and one more thing, the second derivative of natural log of marginal of moment generating function at the point 0 is just variance of x. So this property is important because on the exam, the actual exam, we always have some question about moment generating function, about 2 to 3 questions. This is for sure. Like, we will definitely have a few questions about moment generating function. So make sure you memorize these. Mode and skewness. Even though mode and skewness is not important in the exam, but we do have question about mode and skewness on the exam before. Just like question about D2 is D2 are quite rare on the exam, but still we used to have question about them. So first, the mode of a distribution. The mode is any point M at which the probability or density function of f of x is maximized. And the p percentile of x is basically in statistics, the p percentile is basically a value that separates the data sets, separate the lowest p percent data set and the upper 1 minus p percent data set. So if c is the p percentile of x, then probability that x less than or equal to c is p. We might have one question about percentile on the exam. Like we might have it or we not having it, but usually we have maximum one question about percentile on the exam. Like you're not gonna have 2 questions related to this. The skewness of a distribution. So remember when we work on the distribution, we make the plot or the histogram, either the histogram or this the PDF or the CDF plot. So the skewness of of a distribution is defined by whether the basis mainly focus on the left side or on the right side and are they symmetric. So theoretically, the skewness of a distribution, if the mean of a random variable x is mu and the variance is excuse me, and the variance is sigma squared, then the skewness is defined by expected value of x minus mu whole cube over sigma cube. So if the skewness is positive, the distribution is said to be skewed to the right, and if it negative, the distribution is said to be skewed to the left. If this quantity is 0, we say the distribution is symmetric. So that's what about mode and skewness. Next, inequalities. So in probability, we have a few inequalities that are very commonly used. So I suggest you to go over these inequalities because on the exam, usually we have a lot of questions about inequalities. So the first inequality I want to introduce is Jensen inequality. So if x is a function and x is a random variable such that the second derivative of the function h of x is non-negative, then expected value of h of x is greater or equal to h of e of x. So that means expected value of a function is at least the function of the expected value. And this inequality also applies for trig inequality. So the first one is non-trig inequality. For the second line, this is the trig inequality. So if we have no equal sign here, there's no equal sign here. And this inequality reverse when the second derivative of h of x is negative or less than or equal to 0. So if x, the prime of x less than or equal to 0, then we change this inequality sign to the opposite, less than or equal. And if h of the second derivative of x is strictly negative, then we change it to expected value h of x is strictly less than h of e of x. And we also have Chebyshev inequality. If x is a random variable with mean mu x and standard deviation sigma x, then for any real number r is positive, we have a probability that absolute value of x minus mu of x is greater, strictly greater than r times sigma of x. And this probability is less than or equal to 1 over r squared. 1 over r squared. So these two inequalities are very, very important in exam. So make sure you go over these two. We also have some other results. First of all, for any constants a1, a2, and b, the function x1, x2, we have expected value of this combination a1, x1 of x plus a2, x2 of x plus b is a1 e of x1 of x plus a2 e of x2 of x plus b. And if a and b are two constants, we have variance of ax plus b a squared variance of x. Next, a mixture distribution. Given any finite collection of random variables x1, x2 to xk with density and probability function, say f1 of x, f2 of x to fk of x, where k is a non-negative integer, given the weights alpha 1, alpha 2 to alpha k, where 0 less than alpha I less than or equal to 1. And the function f of x is defined as alpha 1 f1x plus alpha 2 f2x plus dot dot to alpha k fk of x. So in this case, expected value of x to the n is alpha 1 expected value of x1 to the n, and plus alpha 2 expected value x2 to the n plus dot dot to alpha k expected value of xk to the n. So this is applied for the mixture distribution. And and the moment generating function mx of t will be alpha 1 mx1 of t plus alpha 2 mx2 of t plus dot dot to alpha k mxk of t. 1 second. Okay, so that's where everything about this lesson. This lesson is quite short, but the content is difficult. So I suggest you to reread over how to calculate expected value, standard deviation, variance for both discrete and continuous cases. And also the most important parts in this lesson is the moment generation function and inequalities. So make sure you go over all of them. So now let's look at some problems. Problem number 1, let x be a continuous random variable with density function. Calculate the expected value of x. So this is a continuous random variable. This is a very easy problem. So we basically just apply the formula. So we take integral from near infinity to infinity of x times f of x. However, the function is defined from near 2 to 4. So anywhere, any other point, f of x is 0. So we take integral from near 2 to 4. And because the absolute value of function is defined as negative when x is negative and positive when x is positive. So we have to break this integral into two parts. So from negative 2 to 0, absolute value of x is negative x. So this is negative x squared. From 0 to 4, this is x. So you see that this is how we calculate expected value of x. So the answer is 28 over 15. Problem number 2, an insurer annual weather-related loss, x is a random variable with density function. So calculate the difference between the 30th and the 70th percentiles of x. So to find the 30th percentile of x, we have the CDF of x is, remember, like the percentiles, the 30th percentile is basically the point separate the lowest 30% and the highest 70%. So the 30th percentile, before we calculate the percentile, we need to find the CDF. So to find the CDF, we basically integrate the PDF from 200 to x. Here from 200 because the function defined on the interval from 200 to infinity. So the lowest point is 200. So this is easy calculate too. So after you finish integrating this function, we have the CDF is 200 to the power 2 of 2.5 over x to the 2.5 plus 1. So we're going to find the 30th percentile and the 70th percentile and then subtract them. So let's C and D be the 30th and the 70th percentile of x respectively. So 0.3 is negative 200 to the 2.5 over c to the 2.5 plus 1. So c is 230.7. Remember, go back to the slide that we talk about the percentile. So if c is a p percentile, then p equal to f of c, the capital F of c. So we plug c into the CDF, we have the percentile. So here we need to solve for c. So we have c is 230.7, and similarly we have 0.7 is need 200 to the 2.5 over d to the 2.5 plus 1, and d is 223.7. So the difference between these two is 93. Problem number 3, let x be a random variable mean 0 and variance 4. Calculate the largest positive value of probability that absolute value of x greater or equal to 8 according to Chebyshev inequality. So remember the let me recall the Chebyshev inequality. This is the Chebyshev inequality. So we expect to have probability of expected value of x greater or equal to 8. So we compare one by one. This is absolute value of x. This is absolute value of x minus mu x. And mu x is 0. So we have mu x is 0. Sigma x is 4, but we want to have 8 here. So we have to use R 2. So R is 2. So probability x minus 0 is greater than 2 times 4, this probability by Chebyshev inequality is less or equal to 1 over r squared is 2 squared. So this is 1/4. So the largest positive value of this probability is 1/4. So the answer is C. Next, problem 4. If the moment generating function of a random variable x is mx of t, this is equal to 1 over 1 plus t for the third moment of x about the point x equal to 2. So the formula to find the third moment of x about the point x equal to 2 is expected value of x minus 2 whole cube. And we are going to derive this q inside the parenthesis. So this is x cubed minus 6x squared plus 12x minus 8. And this is equal to expected value of x cubed minus 6 expected value of x squared plus 12ax minus 8. And expected value of x cubed is marginal function, the third derivative of the marginal moment generating function at the point 0. Similarly, expected value of x squared is the second derivative of moment generating function x at the point 0, and expected value of x is the first derivative. And we are going to calculate this. So here I have the detailed how to find mx, the third derivative of mx at the point 0, the second derivative of mx at the point 0, and the fourth derivative. So here, because mx of t is 1 over 1 plus t, so m prime x of t is nib 1 over 1 plus t whole square. And then we derive one more time, we have the second derivative. We take the derivative one more time, we have the third derivative. And here we are going to substitute 0 in. So the first term here is 1, and this is 2. It's a nib 6, so we plug it into. Okay, so now we are going to work on the last problem. Let x1, x2, x3 be a random variable from a discrete distribution with probability function. So we are going to determine the moment generating function of my, where y is the product of x1, x2, and x3. So here we are given x1, x2, x3 identical from this distribution. But we are going to define the moment generating function of another variable y. So first of all, we need to define the distribution of y. So here y can be either 1 or 0. Y is 1 if x1 equal to x2 is equal to x3, and this is 1. And y equal to 0 otherwise. So probability that y equal to 1 is probability that x1 equal to 1, probability x2 equal to 1, probability x3 equal to 1, because these three are independent, identical. So probability of y equal to 1 is 8 over 27. So probability of y equal to 0 is 1 minus 8 over 27. So to find the marginal the moment generating function of y, my of t is just expected value of e to the ty. So that is e to the t probability that y equal to 1, e to the 0 probability y equal to 0. So just plug in and we have this is the answer. So that is everything for today. Thank you so much for watching, and I'll see you next time. Bye.